Thank you very much. Thank you for inviting me. It's been really a very interesting day, and I'm sure tomorrow will be as well. Yeah, I'm gonna talk about emotions and all these things, but in robots. And so, why do I mean, um, are these are robots interesting to neuroscientists? What can we offer? Well, you have seen an example by Malware where you can use robots as tools to collect data and to try to understand human affect and cognition. You can also, so sort of stimulus, you can also use AI and robots to try and fit data from the human brain or the animals, etc. But so that's probably what you're most familiar with. But there's other things that we can offer as well. Um, an important thing in robots is that they can link underlying mechanisms, functions, and behavior, and you can see the dynamics of interaction. So they're kind of operational scientific models. So I've been working mostly on simple models. So you're not going to see like very complex models of neural networks that try to imitate human brain or anything like that, simulate rather. But I'm more interested in this dynamics of interaction. And you can say, in a way, my robots have emotions, have some sort of motivational and emotional systems that interact with their decision making. I see them mostly as operational scientific models that can test different theories, platforms for experimentation in ways that you can do with biological systems. And maybe you can see them as well as a new species that are going to live with us soon. But something that I think is important is that they're good to bridge gaps and bring together multiple perspectives and disciplines. So why are emotions interesting for robots? Well, for the same reasons same functions they have in biological systems. So they're, for robots that had to act autonomously, um, in a physical environment or social environment. Well, there are mechanisms for adaptation to deal with important events related to survival. Regulate the internal homeostasis, internal equilibrium, and control interactions with the environment. They motivate and guide action. This is very important for robots to be able to learn what matters, what's important, what to avoid, for example. Also to amplify, motivational systems and to make decisions, and also, of course, value signals for communication. And all this is the case whether you look at robots as creatures that have emotions, or as scientific models, or as a new species that we could study in interesting ways. Okay, so what do I mean by robots that have some sort of emotions? Okay, so I talk about emotions, but I really talk about affect as a model motivation and simple elements of emotion. And I like talking about wanting and liking. So at the very simple level, core affect as a motivation for action, for cognition, for interaction, liking or disliking what we do, perceive, etc., etc. And they're really important for robots as well because they indicate why things matter. So they're kind of driving force. So for autonomous robots as well, for decision making, social interaction, etc. I also take the point that affect and cognition are deeply intertwined, and they maintain affective cognition. And so inspiration I take, so messages I take from kind of you, is that affect provides also useful high impact information. And for example, valence is going to give more information about value, and arousal is going to give more information about urgency of things or the importance of things. And emotions can be different ways of functioning of the same kind of neural system. So in robots as well, core embodied affect is going to ground notions of autonomy, adaptation, social interaction, learning, development, evolution. Okay, so we see them as scientific models. My point of view is kind of embodied affect. So affect happens in and through the body, and in robots, I model this both externally through behavior and expression, but also internally. So I make very simple models or of simulated physiology that has to be controlled homeostatically, artificial hormones that are going to affect, be part of that physiology, etc. So the branch of artificial, or the perspective of artificial intelligence that I take is nothing to do with large language models and these things that you hear a lot at the moment, but it's called embodied artificial intelligence, and well, it's kind of the opposite. So agents are situated in an environment, in interaction, very limited perception of the environment, etc., etc. And we don't try to optimize things, but to keep the robot surviving, to keep their viability, and they have to adapt to different environments. So taking a lot of inspiration from cybernetics as well. Okay, so robots are scientific models. What can we do with them? Well, they can be useful as hypothetical models, for example, for philosophers and neuroscientists too. What if a robot should have, etc., etc. So that's a role they can play. They can be models of specific. We can build models of specific emotional phenomena, such as, for example, fear condition, and we can implement that in a robot and see what happens, what it learns, etc. Models of general emotion principles. For example, we can see emotions as mechanisms to regulate agent-environment interactions, so we can build models of that. We can build models of specific dimensions, emotion dimensions. So, very popular ones in robotics are like multidimensional PAD, pleasure, arousal, dominance models. But we can also isolate the different dimensions and build single-dimensional models and see what are the contributions of arousal only in specific situations, or pleasure, valence, etc. And well, I will argue that the fact that robots are embodied makes a difference with respect to other virtual creatures, for example, virtual agents. They're more like me. They're considered more like me. Okay, so I said that robots can bring together different perspectives, and in my research, I have taken Timberger's program for ethology and try to look at them build models from these different perspectives of mechanism, function, adaptation, development, and evolution. I'm not going to talk about all of it, but give some examples. Okay, mechanisms. So how can we model emotions in robots? So there are different models. The simplest one is, well, actually, emotions are just in the eye of the beholder, and there's nothing inside the robot, but it's just the behavior has the appearance of being emotional. And an example is what is called Breitenberg vehicles. So in my robots, thought experiments by Valentino Breitenberg, a neuroscientist, and they're just responding to external stimuli. So they will have different behaviors of, approaching the stimulus, going away at different speeds or slowing down as a function of how the sensors and the motors are connected. But that's it. Okay. Another type of models are, try to replicate with neural networks, artificial neural networks, natural neural networks. And there's very interesting work in that. The issue there is how to relate functions to structures in artificial neural networks and how they relate to natural ones. Dynamical systems is another type of approach that is very much I is very fond of it. but is mostly used as in a metaphorical sense. So the mathematics get very complex very quickly. So there isn't much, but I would love to see more of that. An approach that I follow is try to modulate, take inspiration from neuromodulation of the underlying nervous system of the robot. So emotions are different functioning modes that allow to more easily integrate emotion and cognition. Okay, so the models I'm going to present are kind of abstract, and we're going to start with the wanting and liking decision making, combining motivational systems and some sort of emotion. Okay, so I often use very simple robots, educational robots, sometimes more complex robots, but for example, Lego robots in this case. And a bunch of people have been working on this with me. So here we have like a typical action selection problem with where a robot has to decide between consuming two resources in the environment in a timely way so that it can survive. Okay, so robots that want, well, the important thing is that the robots have to survive in the environment autonomously. So we can, model something like, two motivations, urges to action based on internal, for example, bodily needs and influenced by external stimuli. So, we've taken this from ethology literature. So they contribute to the maintenance of homeostasis. And they can be bodily, but they can be, cognitive needs, social needs. So we've been applying that kind of model to a bunch of things. So it's very, I don't know if I move, I have this. Does it work? Yeah, okay. So yeah, basically we combine, the effects of the presence of an external stimulus, okay, with the difference of, we have different internal parameters that simulate internal needs, for example, in need for energy or temperature, and they're going to have an ideal value, and then they're going to have the current value, and so the difference is an error, so quite typical model. And the robot is going to try to reduce that error through behavior or through internal processes. So those elements, the error or deficit and the presence, the salience, for example, of the stimulus are going to be combined in a mathematical formula that is at the bottom. And there's different motivations, so we call those motivations, for different needs related to different needs. Here, there's only two, but you can have a bunch of them. And then the robot has different behaviors that allow to satisfy those needs. So the execution of a behavior is going to correct the internal parameters. It's also going to have an effect on the external stimuli. So again, here I just put two, but there can be a bunch of different behaviors to satisfy the same motivation in different ways. So how to choose the motivation? We choose the motivation with the highest intensity. So where the result of that formula gives the highest value. In our analytical strategy, we have more motivations. We can also have what we call voting base, where you make a compromise between motivations and satisfy several goals, several needs at the same time. Okay. So what this gives us is a bunch of is a way to actually quantify what the robot is going to do and how well it's going to allow it to maintain homeostasis. So there's a bunch of metrics that we can use to see how the internal environment is managed. So average maintenance of the variables or variance, etc. But also, taking from ethology, we can see there are cycles of activity So for example, in that environment, it's static and it's a single robot. You're going to have an initial state. The robot is going to have a need higher than the other one. It's going to start looking for a resource, find it, consume it. In B, at some point, the other need is going to become higher motivational density. So it's going to start looking for the other resource, finds it, consumes it, and so on. And so these cycles in this environment are really, very symmetrical. There's no need for emotions. It's really boring. But if you add another robot, things become more interesting because it creates a competitive situation. Because to consume a resource, the robot has to be on top of it. So that already creates a situation where if this robot wants to consume that resource, what does it do? Either push the other away or just run away, depending on maybe its internal state. And this starts looking like, okay, maybe aggressive behavior or fearful behavior. We can see this as a attention problem. So looking at the right thing. Okay, so if we look at the activity cycles, we can see this creates a more difficult situation and a problem because they're not symmetrical anymore, and they just go, to the zone where they're going to reach very easily the limit. So the variables have to be kept within a permissible range. So it's going to get to the limit where the robot could die if it reaches the limit. So we identified two main problems. One is goal interference. The other robot is on the resource, or over-opportunism, giving up too often and going to look for another resource. So if we treat that as maybe attentional problem, it can be, we can modulate it with a stimulated hormone where we change actually, the way the tactile, sorry, okay. What I didn't see, say is that, so the robot can detect things that are in contact with it, with that yellow part that is at the front. And it has also an infrared sensor to detect the other robot. But that's it. Okay. So change the way that sensor, tactile sensor works. So instead of withdrawing when it detects something, it's going to not do that. Or it can change the salience of the stimuli and increase the salience of what's important and decrease the salience of what's not important. And we can achieve that with that formula, just adding a weighting factor that could be controlled by a hormone, for example. Okay. So that is going to create. I'm going to show the video very quickly. So that's what the robots are doing. So they don't communicate that each of them is just solving their own two resource problem. Let's see if I can just speed it up because otherwise it's very long. Okay, so most of the time they're not doing anything together, but okay, sorry. So they have met the resource there. Okay, so one of them is kind of weaker. It's just the bumper is working in the usual way, has bumped into something, which is the other robot, and has backed away. Okay, here we have another case where actually that's not going to happen. So the hormone has changed the way the bumper works and is not going to back away. And you see they engage in that behavior that emerges no program. It's just as a function of their morphology, their internal state, and the interaction. Okay, so that's kind of the simplified basic model underlying what I'm going to present. But we can have a look, for example, at those activity cycles that you can see, you can track in the internal physiology, the variables, the values of the variables, and you see that without the hormone are a lot more asymmetric. The problem is harder, but the hormone helps to actually control and manage better. And as I said, there's other metrics based on how well the internal environment is maintained that we can use. Okay, what happens if we change the role of one of those robots? And so one of them becomes a prey and the other a predator, and we add things so that they can interact as well. So one of them, the prey is going to have one more internal variable, their integrity. The predator can attack the prey, and the prey will lose integrity. Okay. So would that model, that architecture, as we call it, of decision making work in this case? Well, probably not, because the prey is only going to go away when it's been attacked by the predator. So it needs some sort of anticipation. And again, we can take inspiration from the behavioral hormones, the temporal dynamics in this case, and there would be like a concentration of the hormone that would increase with exposure to the other robot. And in this case, it would not modulate the perception of external stimuli, but the perception of one of the internal variables, the integrity. And what is going to happen here is that the escape behavior eventually with exposure is going to be triggered before it's attacked. And therefore, it's going to be more it's going to have that kind of very simple anticipation and survive better. Okay, so that's the one thing. The liking, the simplest way of simulating the liking, pleasure, is actually seeing what the behaviors do to manage the homeostatic variables. And so behaviors that actually correct the errors towards the ideal value, which is in the kind of the center. So decreased errors would be positive. We could say will be pleasurable, and to the contrary, if they take the values away and close to the fatal limits, they're going to be noxious. Okay, so pleasure is going to, in that formula, again, affect the perceptual element of motivation, so the incentive salience. And what we saw in experiments is that actually can improve the viability by influencing persistence and opportunism, so the trade-off between those two. Also, the excess of opportunism that can lead to impulsivity. So we can actually also model the dysfunction, and excess of persistence, maybe addiction and compulsion. Okay, so this is an example of experiments that we did, where the robot has, in this case, a humanoid, has to choose between consuming two resources, and we arrange them in different ways, symmetrically, but they're difficult to find. The robot has to move actually to find them, or asymmetrically, so more than one and than the other one. And we also play with the pleasure the different stimuli provide. So two kinds of pleasure, one linked to the satisfaction of the need, but we also wanted to study other types of pleasure. So we just added extra pleasure in some conditions given by just the fact of consuming the resource. So no, or it could be seen as sensory pleasure. So unrelated to satisfying a need. So we, created different conditions, and what I wanted just to show, were environments asymmetrical or asymmetrical, and the pleasure is symmetrical or asymmetrical. But I just wanted to show that actually by looking at, these activity cycles traced on the physiological space of the robot, you can actually see the effects, for example, in condition 4, which is asymmetrical environment, and asymmetric pleasure, where there's more pleasure on the scarce resource. That extra pleasure has like a balancing effect, so a positive effect where there's a better balance between both. Whereas in condition 5, for example, where pleasure is associated, extra pleasure is associated with more abundant one, is, you can see the values go up to the fatal limit of 100. So it actually makes the situation worse, the management worse. Okay. So this kind of signals can be used for a bunch of things. For example, to learn affordances of objects, so that the robot can learn that autonomously, or affective landmarks. For example, here using this pleasure, um, you know, how the deficits are corrected, etc. Here we could use arousal. We use arousal, to learn what happened in different locations in a place, so that the robot then can avoid them or look for them. High arousal, which too unpredictable. Arousal is linked to novelty detection. Like medium arousal is fine, or too low, that is like boring, unmotivating. Okay. So this kind of model can also be applied to social robots. And here is an example of a companion robot that we did for children with diabetes to try to help them understand the condition, but also increase self-confidence. And so the robot has a model of diabetes, and the children had to play with the robot to look after it, and the robot would show some symptoms. The child would have to try and correct the symptoms. You could inject insulin with a like Bluetooth device, or give corrections foods of this type or the other, etc. And the experience would always be positive in the end. So to give them a mastery experience where they could actually help someone, a robot, and increase their self-confidence, that they actually understood the condition. But I just wanted to show the kind of underlying architecture is the same kinds of some motivations, in this case, including to socialize, some related to diabetes, eating or tiredness, etc., to play. So it's the same kind of model, basically. Okay. So there's a video on my website if you're interested. I'm not going to have time to show it, but explaining a little bit. This we also model this when emotions could be maladaptive, for example, in compulsive behavior, as I said, in decision making. And we tried to implement different theories about compulsive behavior. So one cybernetic model based on what is called signal attenuation, so the perception of, okay, the need has been satisfied, there's no error anymore, you can stop the behavior that doesn't happen, the behavior to satisfy the need that doesn't happen. So that's one of the models. Resorting to habits in the wrong context, or the role of anxiety. So we combined, we tested the 3 models. I'm going to show a model of stress-induced compulsive behavior, where there was the robot had a tendency, but is not tendency to develop compulsive behavior depending on its internal state. Some internal variables had a tendency, and the fact that a stressor happened, but not in every case, the stressor would trigger it anyway. So I'm just going to show the video because I'm running out of time. Okay, so here, we took inspiration also from animal behavior, and so this is a robot that has to maintain its energy, so it has to eat, but also keep its integument and groom its integument, like feathers or something. So on the left we see, that is grooming, that behavior, and the white spot is food. On the right, we see the robot has been trapped, and that is a stressor, an external stressor, because it cannot move. So that is really that is increasing it. Stress is releasing like a stress hormone that is interacting with other variables that regulate the internal hemostatic needs. So you're gonna see it could eat, so that wasn't a problem, but so it's gonna go to groom, and then it is not going to be able to stop, and it's going to die. And then we were also interested in trying to model some interventions. Okay, so when to to try and help psychiatrists understand, okay, if I apply this treatment at this point, is it going to increase stress? Is it going to make things worse? Or, just preventing systematically, or letting the robot do the compulsive behavior for a bit. And so again, we can inspect the different conditions, the effects on the different conditions on stress, and how the internal environment is maintained. I am going to skip modeling pain. Just say a word about development of affective bonds. So we've done quite a bit of work on modeling attachment, together with comparative psychologists and developmental psychologists, and a model for of attachment that could kind of based on attachment in human and non-human primates. Here, what we have is two different caregiving styles, two different caregivers. The robot has to learn an environment, and that's stressful. The novelty is going to stress it, and we have two very different behaviors. One is going to help the robot, is coaching the robot. The other one is just leaving the robot to learn independently. Okay, so that is going to have the effect that the robot with the caretaker that is attending, it's going to learn that environment more quickly. So the arousal of the robot, novelty produces arousal, that is going to affect a parameter, the learning rate of the neural network. Okay, the other one has to control, itself, and is going to learn that environment more slowly. But when put on new environments, is going to be the opposite. So the independent one, the one that was left alone, could learn new environments more quickly. Very quickly, you want the robot also to adapt to different interaction styles. And so here we have, like, is the toddler, the robot companion for children with diabetes. Anyway, so here we have it with a caregiver that is satisfying all the needs, is there all the time, and is very expressive. It's like annoying. Here, after a while, it's been interacting with this other caregiver that is much more independent again, on the same needs, the same kind of, the expression is very different. So the robot has, by using just the feedback from the caregiver, has kind of learned to adapt from one to the other, just by using like the how often it shows the face, how it touches. And you might have heard he was very happy because that event is really rare. So it was something that was salient. And okay, and yet last video, we can add a layer here and actually develop the neural network, the robot, in interaction with humans or with its environment. So here, basically, we have another layer, like we call an epigenetic model, inspired from that, where there's another set of hormones that are going to regulate, their own receptors. Basically, okay, the same kind of architecture, same architecture is going to give rise to two very different behavioral phenotypes. depending on how the human interacts with the robot. So we have, an attentive caregiver that is, stimulating the robot very smoothly, making sure that, all the sensors are stimulated, exposing to different textures slowly so that the neural network can converge, and the opposite there. And so we have very different behaviors that develop. So, on the left, we have the robot that developed with the like the attentive caregiver, very playful. It develops a lot more behaviors. It wants more of that stimulus. The other one is trying to avoid the human. The human just a pattern of movement detected with like infrared sensors, but it's trying to go to safe areas where there's no movement. Okay, we can see that different networks develop in different environments, like very little stimulation, more a richer environment, etc. Okay, so I'm going to conclude here, and I just like to thank the different collaborators, my students, and funding institutions, and all of you for your attention. Thank you.